Alright, hi guys. We'll be covering the turning effect of forces. This is chapter 5, or in your syllabus is actually your chapter number 4, right? Just in our notes is chapter 5. Right. So before we talk about turning effect of forces, there are a few things that I want to remind you of what forces can do. So if you recall, forces can do a few things. One, forces can cause, from your previous study lah, forces can cause things to accelerate or can cause them to decelerate. It can cause them to change direction. It can also cause them to change the shape of an object if you deform it. So these are all the effect of forces. But there's another thing that force can do that we haven't considered. And that is in the case of a seesaw kind of situation. What happens when I exert a force in this direction and it is held in place here? Right, then you know that the object in a seesaw situation, this seesaw will actually rotate in this direction. So now we are covering, instead of just linear motion, that means just left, right, and also just the change of direction, we are now focusing a little bit on the direction and what it means for a force to cause a change in the direction of something. Alright, so you will hear this term being used a lot, so I think we better get used to it. The term is moments. Moments is something, it's called the turning effect, or rather a measure of the turning effect of forces. Alright, so I have a short video to show you. Alright, it's a video of I'm sure you know this channel. It's called a Crazy Russian Hacker. So if you see, instead of just using your hand to turn open a jar, he's using a device to actually exert the force at a greater distance, and then makes it easier for you to then open a certain jar, open the lid of a certain jar. So I'm sure we are all very used to a seesaw kind of situation. Obviously, if the seesaw is centered around here, around the center of the seesaw, and the golf ball is causing the seesaw to tilt to this side, even when the rubber ducky is here, then you know that the seesaw is much heavier or weighs more than the rubber ducky. So the question is then, how do I make the seesaw balance without changing, without adding more things onto the seesaw itself? How can I just change the positions or change anything about the seesaw to make it such that it's balanced? So some of you may naturally say that I would want to move the golf ball a bit more closer towards here in this direction. Right, some of you may also say that I can also move the pivot closer towards the golf ball, and then that will also cause, if I find the correct position, the seesaw to be balanced. Now, so you are exactly correct. The golf ball can be moved closer to the center of the board, or I can move the pivot closer to the golf ball. So now we are going to explain the science behind why all of this works and what is it, how is it that we can explain how an object can be balanced. Alright, so as we know, forces can change the direction of things. So we call this effect of the forces the turning effect of forces. Alright, this turning effect is also known simply by the word the moment. Alright, in this kind of system, it is basically a lever system. Alright, and of course a lever system will consist of something called a pivot. A pivot is also sometimes known as a fulcrum. So the pivot in a seesaw situation is the center of the thing lah, where the seesaw will just rotate up and down. So that is called the pivot. Right, so why study moment? Because we need to be able to quantify how a moment is able to help us move things, or how it is able to cause us to make our life easier. Alright, so whenever you have a tin like this, right, if you're gonna try to just use your hand to rip out the cover or the lid of the tin, it's going to be very, very difficult to do. In fact, most people, what they will do is they use a spoon, they dig the edge of the spoon into the underneath the lid, and then they will then use the spoon to kind of force it open. So this works on the principle of the turning effect of forces, otherwise also known as moments. Now, so let's discuss what exactly moments are. Moment, or rather moments or turning effect or the force, is proportional to two things. One is the magnitude of the force. How much force I'm applying, the greater the turning effect, or the greater the effect of the turn of the force. The second thing is the place where we exert the force matters. Alright, and I need you to note the particular phrasing because you will need to get used to it. I'll give you a better phrasing later on, but basically the distance or the position that you exert the force, which is the perpendicular distance from the pivot to where you are applying the force, it matters. So it is proportional to these two things. Alright, so this slide is a very important slide. Let's talk about a few things first. One, the definition. The definition of the moment of a force. The moment of a force is also sometimes known as torque. So it is either referred to as the moment, turning effect of force, or the torque. All of these three mean equivalent things. The moment of a force is the product. That means I multiply two things. One, I multiply the force, and two, the perpendicular distance d from the pivot to the line of action of the force. So I'm going to detail what each of these terms means later, but just a short, I'm going to shorthand a lot of things in this chapter, so just get used to it. I'm going to abbreviate line of action of force as LOA of force. Line of action of force. I will also going to abbreviate, you're going to see me do this a lot. The perpendicular distance will just be this. The mathematical symbol for perpendicular and D. Either big D or small d. Right, sometimes, so the formula is given by this. Moment equals to force times distance. Now, I like to write the formula instead like this. Moments equals to force times perpendicular distance. Because there is another quantity that you're going to learn later on in energy, which is also exactly force times distance. So we need to make a distinction between the two. So I usually write it like this. Now, of course, we'll do just some unit analysis. Force is given in newtons. Distance is given in meters. You multiply the two of them. Therefore, the unit of moments is Newton meter. Now, can I give it in any other units? Yes, you can. Because distance can also be given in cm, which means I can also give the unit of moments in Newton cm if need be. Alright, so let's unpack what force, what is this d here. This d here, or the perpendicular distance, take note the notation I use, is the perpendicular distance from the pivot to the line of action of the force. Alright, let me run through all the things first before I talk, before I stress on what this is. The unit, the SI unit is Newton meter, but of course you know you can alternatively also use Newton cm if your distance is in cm. Alright, it is a vector quantity because we are talking about the direction. So we refer to the direction of a moment as either clockwise or anti-clockwise. Now I need you to be very clear and use this kind of notation to describe the direction. Oftentimes students will say things like the right side of the seesaw go up and the left side of the seesaw go down. This is all not very good explanations of the direction, the way an object turns. So when you're going to talk about how an object turns, please use clockwise and anti-clockwise. And then of course my abbreviation for them is also here, CW and ACW. Now let's talk about this moments here. What on earth is this thing? Perpendicular distance from line of action of the force to the pivot. I know some of you may be struggling and thinking, why does it even matter? Alright, it matters, this factor here matters, and not only how much force I'm applying, because I can apply a force, the same force at the same position, but when I do it in two entirely different directions, it can have two totally different effects on the turning effect. So that means how strongly the seesaw will turn based on how or where, or rather where I exert the force and in which direction I exert the force. Of course, you know that this is going to produce a greater turning effect than this one over here. And now we are going to use the formula here, moments equals to force times perpendicular distance, to explain why there is a difference in the turning effect. Alright, before we go into that, I want to discuss a little bit about what a pivot is. So I have with me here a meter ruler and I'm rotating it. So there is a turning effect on the force. There is a turning effect of forces or moments which is causing this to rotate in either the clockwise or anti-clockwise direction. Now, the pivot point is defined as the point around which the rotation occurs. You will see that actually when I'm rotating it like this, you naturally can tell me my finger is where the pivot is. It is the point through which the rotation occurs. The rotation happens around this center point. Now, oftentimes you can also have an easier time thinking about the pivot in situations where the pivot is not easy to identify as the point that does not move in any kind of rotation. So if you look at it, every part of this ruler here is moving up and down, and the same as over there is moving up and down. Only this one point remains in the same position when the rotation occurs. So oftentimes it is also not 100% of the time, but most of the time this point that doesn't move is also the pivot. So this is how we identify the pivot, and identifying the pivot is the very first important step in calculation of moments. Right, so now that I am clear on what this term is in the definition, which is the pivot, this is just one part of finding this perpendicular distance of the line of action of force to the pivot. So now we need to talk about finding the line of action of the force or the pivot and what it means for it to be the perpendicular distance. So let's have a look. In a normal kind of seesaw situation like this, if I ask you how far away is this force on the right here, force A, how far away is this force acting on the away from the pivot? Naturally, most of you will be able to tell me this is the distance. And this distance is, you are rightly pointed out, is the perpendicular distance. Now, the difficulty comes about when it is not acting perpendicularly, the force. Right? What happens if the force, instead of acting in this direction, is acting at an angle to the seesaw? Then what are you going to do? Alright? So, how I define this, because obviously this and this, even though if they are both 10 Newton forces, will have a different effect on the turning. So we define the perpendicular distance as the difference in the calculation for the calculation of moments, which is force times perpendicular distance. So let's look at how to identify perpendicular distance of this red line. So there are two steps, and I've summarized the step here. Draw the line of action of the force by extending the force line. 2. Find the shortest distance between the line of action and the pivot. So if I follow step 1, I extend the force. So by extending the force line in both directions, I have now formed what I call the line of action of force. Right? It sounds complicated, but it's not. This is the direction of the force. This is the line along which the force acts on. So I say again, this is the line, or rather the direction in which the force acts on, or the line that in which it acts on. So all I now need to know, if you look at the definition, is the perpendicular distance between the line of action of the force and the pivot point here. So the perpendicular distance is the shortest distance between this line and this point. And the shortest distance is found by forming a line that is 90 degrees to this line, but also hitting the pivot. When I do this, I identify the perpendicular distance. So therefore, I can then use the formula for moment equals to force times perpendicular distance in calculation of the moments. But the perpendicular distance for this force is using this. So this is how I deal with moments. Alright, so how to identify or calculate moments? First most important thing is identify where is the pivot. The second important thing is where you need to find is the line of action of force to pivot. This is the perpendicular distance. And once I know where the pivot is, I can therefore find this point number 2, which is the perpendicular distance, provided I follow these two steps here. So once I found that, then I just need to simply apply force times perpendicular distance to then calculate the moments. Alright, so let's just do a little bit of practice. Can you identify the perpendicular distance here? Alright, naturally most of you very easily, because all of them are perpendicular. So let's just follow and run through the steps. Step 1, extend the line of action of the force. Find the shortest distance by finding the shortest distance between this line and the pivot point is the perpendicular distance, and the shortest distance is here to here. Alright, it is the line that is always perpendicular and hits. So I can do the same here. This is perpendicular distance for force C. This is the perpendicular distance for force A, and the perpendicular distance for force B, just be careful, it's not from here to here, it's from here to the pivot. This is perpendicular distance B. Right? So you can see it here. This is how you can find perpendicular distances. Alright. Just a example here. We need to do a little bit of practice. How do I find the perpendicular distance of force A? So I just extend the line again. The shortest distance between this and this will give me the perpendicular distance. So naturally it's just something like this. It will form a 90 degree and hit the pivot. This is the perpendicular distance. Alright. Now, for some of you who struggle with this, then there is also a surefire way by using just a ruler to find. Alright, so if I were to look at it, I've drawn the line of action. I know where the pivot is. If you are struggling with the perpendicular distance, then all you need to do is put your ruler down onto the line. Make sure the one of the edges is sitting directly on the line, and then you slide. You slide, you slide, you slide until the ruler hits the pivot. Then this is the perpendicular distance, because then you will form a 90 degree line. Now, why is this perpendicular distance the shortest distance? Because any other line that connects the pivot to this will be a greater distance. So for example, let's say I say this line. If I draw this here, this is definitely a greater distance than this one. So the perpendicular distance is actually the shortest distance from this line of action to the pivot. Alright, so there's some example. So how do you find the perpendicular distance of force B? Again, very simply, just extend the line, the shortest distance. Again, if you are struggling with this, just put your ruler there and slide it along until it hits the pivot. When it hits the pivot, this is the perpendicular distance. Alright, then simply you need to measure this, or if this is given, then you can just use moment equals to force times perpendicular distance to calculate. Alright, so let's look at this. So now that we know how to calculate moments, the moments to fully describe a moment, because it is something that causes a change in direction, you must be able to tell me, or rather describe what is the direction that the object turns, or rather what is the effect of the moment. So any clockwise moment is defined as a clockwise moment when it causes a clockwise rotation, and an anti-clockwise moment is defined as an anti-clockwise moment when it causes the object to spin in an anti-clockwise direction. So normal seesaw situation, let's just identify whether they are anti-clockwise or clockwise moments. So let's start from here. This will cause the object to turn this way, so this is actually a clockwise direction, clockwise moment. This is therefore this is also clockwise moment. It will cause the seesaw to rotate in this direction. If I think about it this way and I pull it this way, then I'm expecting that the seesaw will actually turn down like this. This is from here to here. Again, here to here is an anti-clockwise direction. Anti-clockwise moment. Anti-clockwise moment. Alright. Over here, if I pull it up, the seesaw will turn this way. Turn this way. So this is an anti-clockwise direction. So anti-clockwise moment, anti-clockwise moment, and this one will cause this fella to turn here, so clockwise moment, and here as well clockwise moment. Now, what happens if I have a force that is acting like that in this direction, and that is my pivot? Now, is it easy for you to identify whether it's a clockwise moment or anti-clockwise moment? It's not as easy as you think. So if you are going to have trouble, then you fall back on the two steps. Step 1, extend the line of action of the force. Basically just extending the force in both directions. The shortest distance between this line and the pivot is the perpendicular distance. Since this line of action actually hits the pivot, you know therefore this perpendicular distance is actually 0, because the distance between them is actually 0 meters. The same goes with this. If you're going to have trouble thinking about whether it's going to cause a clockwise or anti-clockwise, my suggestion is just draw the line of action of the force. If it coincides, that means the distance between this line of action and this pivot is actually 0. So the perpendicular distance for this one is also 0. Alright, so whenever the line of action of the force passes through the pivot or coincides with the pivot, then the perpendicular distance is 0. And because the perpendicular distance is 0 and your moment's formula is given by force times perpendicular distance, and this fella is 0, that means my moment is also 0. So because my moment is 0, therefore I have 0 turning effect. It doesn't turn. The object doesn't feel any need to turn, or doesn't feel the need to turn because of the force. Alright, so let's run through again some examples. This force will cause this object to turn in this way. This is the anti-clockwise direction. This fellow will cause it to turn this way. This is also the anti-clockwise direction, and this is the clockwise direction. Again, this one is acting on the pivot, which means there's actually 0 moment. So how do you explain why there is no rotation, or rather why there is no turning effect? So this is the explanation. There's 0 moment because the perpendicular distance from the line of action of force to the pivot is 0. And because moment equals to force times perpendicular distance, and perpendicular distance is 0, my moments is 0. And therefore there's no turning effect. Alright, so this is the solution. You can pause if you want to have a look. Alright, just also do take note that some of the questions may actually be the first time you encounter in the O-level chapter as a 3D problem. So you have a door drawn like this, and they say a girl exerts a force of 10 newtons on the door handle, which is located here. Which means actually the girl is either pushing the door this way or pushing the door this way into. So it's actually a 3D problem. It may be the first thing. So you need to get used to encountering 3-dimensional problems actually in the O levels. So step 1, I need to find the pivot. Remember, step 1 is determine the pivot. So in this case, it is easy. The hinges are the points of the door that doesn't move. So I know that the hinges are the pivot. Step 2, I need to determine the perpendicular distance. Alright, so how do I find perpendicular distance? The force is exerted in this direction. The line of action is along this force where my pen is. Therefore, the shortest distance between the hinge and this line is actually this distance, which is the 1 meter distance. So how to calculate the moment? The force is 10 newtons here. 10 times 1. Answer 10 newton meters. Easy. Now, if I want to be extra, can I change the force? I mean, the force remains as 10. Can I change the distance to 100 cm instead of 1 meter? Sure, by all means. Which means then your answer is then 1000 Newton cm, because your force is in newtons. Now, this may also be a convenient time for me to remind you that sometimes finding the perpendicular distance, or rather it lends very easy to trigonometric, trigonometry. So, Tuakaso, you learn this in lower sec. Because of the nature of the perpendicular distance, one of the angle is always a right angle triangle, right angle, so it lends itself to trigonometry and right angle triangles. So just a refresher, Tuakaso, the opposite direction here, or the opposite side to the certain angle, is called the opposite side. The longest side in a right angle triangle is called the hypotenuse. The side that is not the opposite of hypotenuse is called the adjacent. So Tuakaso means tangent theta, which is O and A, is equals to opposite over adjacent. Cosine A and H is adjacent over hypotenuse, and so SOH sine is opposite over hypotenuse. So in doing so, if they give you, let's say, the hypotenuse and you need to find the opposite as the perpendicular distance in your question, depending on the question, then you can use theta opposite and hypotenuse, which is so you can find sine theta equals to opposite hypotenuse to find one of the sides. This is in case it lends itself quite easy for them to integrate the trigonometry into this kind of moments question. So just a refresher that I thought may be useful here for you. Alright, so this is the solutions. Alright, we come now to what we call the principle of moments. Now, so if I'm given any situation where there's a rotation, and I'm given a pivot, I'm given a force, I know exactly how to find the moment. And I know exactly whether it's going to cause an anti-clockwise or clockwise moment. Now, the principle of moment is then something else. The principle of moment states that if the lever does not rotate, that means the turning, it doesn't turn at all. It means that even though there are forces that by right should cause it to rotate, right? When the lever doesn't rotate, then it means that the clockwise moment caused by the forces must be equal to the anti-clockwise forces, or rather moments by the other forces. So the moments will cancel out each other and cause the lever to be balanced. Alright? So the principle of moments, I'm going to skip past this. The principle of moments, this is important. This is a definition. You definitely need to remember this. The principle of moments states this. States that when a body is in equilibrium means it's not rotating. This is important. It must be there. When an object is in equilibrium, the sum of the clockwise moments about a pivot is equal to the sum of the anti-clockwise moment about the same pivot. Now, why do you say sum? Because in any moments question, they can give you as many forces as they want. It may not even just be two forces, one causing anti-clockwise and one causing clockwise moment. They could give you 2 or 3 forces, some of them causing clockwise moments, some of them causing anti-clockwise moments. So you need to figure out whether they are clockwise and anti-clockwise. And when they tell you the object is balanced, or rather is in equilibrium, then you need to sum up all the clockwise moments and make sure that it is equal to the sum of all the anti-clockwise moments. Now, just some notation I need to take note. I use this kind of notation quite often. This is the mathematical symbol for sum of. So I will say sum of clockwise moment equals to sum of anti-clockwise moment. So this is called the principle of moments. And then in equilibrium, this is true. And the important point is that it must be about the same pivot. So in principle of moment, the sum of clockwise moment is equal to the sum of anti-clockwise moment about the same pivot. Now, what if it's not equal? What if the clockwise moment is not equal to the anti-clockwise moment? Then obviously, if the clockwise moment is more, then the object is going to rotate in the clockwise direction. If the anti-clockwise moment is more, then the object is going to rotate in the anti-clockwise moment. So, for the principle of moments, they are equal when the object is in equilibrium. So all these are important points. You miss out any of this equilibrium, sum of, same pivot, you're going to get the definition wrong for this. Alright, so let's talk about this. There are 2 conditions for true equilibrium. You learn in chapter 2 when we're talking about Newton's law, or rather Newton's first law. It says that when an object has a resultant force of 0, then the object doesn't move. So when an object has resultant force of 0, it doesn't move. That's Newton's first law. Now, for an object to have true equilibrium, or rather we call it, this is related to what we call translational. That means it moves either left, right, up, down. So for rotational equilibrium to happen, then, or rather rotational equilibrium or full stationary to happen, the resultant moment must also be 0. So let me give you an example where the resultant force is 0, but the resultant moment is not 0. So if I have an object like so, I exert a force upwards of 2 newtons, and I exert a force upwards of downwards like that, 2 newtons. Obviously, if I'm going to look at the forces, I just say resultant force. The resultant force, you know, is going to be 0 newtons. But is the object going to rotate? Obviously, you know that when I pull it this way and I pull this way, you're going to expect this object to rotate in this direction. For example, just like this. I pull it up this way, I pull it down this way, and then the object is going to rotate. So this object is not having a true equilibrium, or rather a full equilibrium. For a full equilibrium to happen, the resultant moment must also be 0. Alright, so let's just look at the question on the principle of moments. So, what is the sum of the clockwise moments? few things you must know when you're finding the clockwise moments. You look at all the forces, identify first whether it is a clockwise moment or anti-clockwise moment. So this is going to cause a rotation like this is going to cause a rotation like that, this is going to cause a rotation like this, and this is going to cause a rotation like this. So I know immediately these are clockwise and these are anti-clockwise moments. Alright, so what is the sum of the clockwise moments? The sum of the clockwise moments is therefore just 10 multiplied by this perpendicular distance, 10 times 0.6, plus this one also. This is also a clockwise moment. Now, do not be tricked, because I know a lot of students are going to put this. They're going to just put 5 Newton times 0.4, because they naturally just see 0.4 and put it in. But remember, the definition of moment is force times perpendicular distance from the line of action of this force to the pivot, which is here. So actually, it's not only 0.4, it's a full 1 meter. Alright, and then that will give you the answer for the sum of clockwise moments. Do the same for the anti-clockwise moments. The anti-clockwise moments, 2 times 0.5 plus 8 times 1 meter. Alright, so then you do the calculation. So this will give you a value of 11 Newton meters, and this will give you a value of 9 Newton meters. I believe my calculation is correct. So obviously you see the clockwise moment, there's 11 Newton meters. Anti-clockwise moment, there's 9 Newton meters. They ask you what is the net moment or the resultant moment. The resultant moment is going to be 11 minus 9. It is 2 Newton meters, and you must tell me which direction. In the clockwise direction. Alright, so is the beam balanced? No, because I have a resultant moment, so I'm not going to have a balance. Rather a beam that is balanced. If not, which direction will it turn? It will turn in the clockwise direction. Alright, so here are a few steps that you may want that may be useful to you. If it's a principle of moment question, then it becomes useful to them for you to first find what is the pivot. Step 1. So in this kind of question, I'm going to identify this. Yes, I have identified the pivot. Step 2, find all the forces that are acting. So I identified this is force 1, force 2, force 3, force 4. So once I've identified all the forces, find out what is the action of the force, whether it's going to cause a clockwise or anti-clockwise. So just now that's what I did. I said this is clockwise, this is clockwise, this is anti-clockwise, this is anti-clockwise. So I just take note which one is clockwise moments, which one will cause clockwise moments, which will cause anti-clockwise moments. Then I find the perpendicular distance for each of them. Remember, do not be careless. You must find the perpendicular distance of each of them. And then basically what I do is I sum up the clockwise moments, which is step A here, which is what I did. Find all the clockwise moments, find all the anti-clockwise moments. If the object is in equilibrium, then the clockwise moment must equals to anti-clockwise moment, which then becomes powerful, because let's say if I do not know this, I can actually find what is the force exerted here for the object to be at proper equilibrium or rotational equilibrium. Alright, so these are the solutions. You can pause to have a look at it. Alright, so let's look at this question here. The object is in equilibrium, which means the object is balanced. So taking moments about the pivot, let's do these questions together. You can pause and attempt the question first before you hear out my solution. Alright, so if you're ready, let's go. First, step 1, find the pivot. Step 2, identify all the forces. I see 3 forces here, so I've identified all the forces. Find the action of the force, whether it causes clockwise moments or anti-clockwise moments. This one is clockwise moment, this one is as well clockwise moment, and this is anti-clockwise moments. Then I find the perpendicular distance. I know that this is the perpendicular distance for this one, this is the perpendicular distance for this one, and this is the perpendicular distance for this one. So I sum up all the clockwise and I sum up all the anti-clockwise. So the clockwise moments are 0.6 multiplied by 6. This is this force. Alright, plus 4 times 1 meter. 4 newtons times a total of 0.6 plus 0.4, which is 1 meter, equals to the sum of anti-clockwise, which is equals to 0.8 times force. So because they are in equilibrium, I can make this statement that they is equal, which means I can then find the unknown force. So do your calculation and you can find that the force is equivalent to 9.5 newtons. Right, so I'm just going to move that question down so you can have a look at the answer. You can pause if you need to have a look at the solutions. but that's the solution that I worked out. Now, what about this question? Okay, have a read. I have a uniform plank of length 1 meter, weight 30 Newton, rest on a wheel at one end. So I need to determine the force. So first off, I need to determine where's the pivot. Look at this. If I exert a force here, I'm expecting this wheelbarrow to rotate in a certain direction. Where's the point that doesn't move? I have identified this as the point that doesn't move. So this is the pivot. Right, so I like to draw a triangle there to help me imagine. Determine the minimum force needed by the farmer to lift the plank, which is loaded with 50 newtons of apple in the middle, such that the plank is horizontal. So when they say that the plank is horizontal, or they're asking you to find the minimum force, what they're saying is that is the force that just manages to balance this, which means I'm talking about an object being in equilibrium. Alright, now this is going to be new. So far, all of your planks or the things, or rather the part of the lever you're talking about, has no weight. They always say it's negligible mass, or we have assumed it's negligible mass. Now the plank or the leverage system actually has a mass. So 30 newtons, you need to factor in this. Step 2, remember, is identify all the forces after finding all the pivot. I know this is one of the forces. I know that the 50 Newton force is going to act downwards in this direction. And it's a 1 meter plank. Then the weight is actually, weight of the plank, which is 30 newtons, is also going to act from the same position. I just draw it a little bit displaced so that you can actually see where is it. And we call this the center of gravity. And we're going to talk about this in a while. Right? So basically, now I've identified the 3 forces, 1, 2, and 3. This one is going to cause the plank to rotate this way, same as this. So these are 2 clockwise movements. And it's going to cause this one, this is anti-clockwise movement. So all I need to do then is to calculate. Because it is at equilibrium, or rather the force just, minimum force just needed, that means just enough to balance it. I can then do the sum of clockwise equals to sum of anti-clockwise. So I have 50 newtons from the apple times 0.5 plus 30 newtons from the apple times 0.5. This is clockwise movements. So it's 50 times 0.5 plus 30 newtons from the plank itself times 0.5. Then this must then be equals to the force exerted by the guy, but the perpendicular distance for this guy is actually 1 meter from the pivot to the line of action of the force here, times 1. So then I can then find the force. And the answer for this is actually 40 newtons. Alright, so that's how we deal with questions of this nature. Alright, so this is a summary. This is the definition of a moment. You need to memorize this. You need to get familiar with this perpendicular line. You cannot just say perpendicular distance without telling me this portion. You're going to get this definition wrong. Right? So the pivot to the line of action of the force is important. Then the principle of moment states that when an object is in equilibrium, or rather is balanced, the sum of the clockwise moments must equal to the sum of the anti-clockwise moment about the same pivot. This is also important. Alright. Alright, which brings me to the second half of this chapter, which is talking about center of gravity and stability. So let's talk about what center of gravity is. The center of gravity of an object is an imaginary point where it seems like where all the weight of the object seems to act from. Alright, so I'll explain a little bit what this means. So a center of gravity, it means that I can replace all the, obviously an object is made up of all its small little parts here, right? So each of them will have its small little weights acting in certain direction downwards because of the force of gravity. Now, what we're saying is that the center of gravity is a singular point on any object depending on its shape, and we can say that the weight of the whole object seems to act from that point. Alright, why is that so? Because you imagine if I, instead of using this black string here, I have a purple string only. Alright, this blue string only. When I release this object, of course you're going to expect this object to rotate in this direction and hang downwards there. Alright, and the same if I have nothing here and I only have the red string, then of course you're going to expect the object to rotate in this direction and hang like this. Now, there is only one point where you hang it, it will remain in a certain position. Right, so that position is at the position where it balances out all the weight from both sides, is the center point of the object. So this center point of the object is called the center of gravity, and the weight seems to be acting from that one single point. So it becomes useful for us in our calculation of weight using moments, or rather moments using weight. Alright, so we can replace all the individual particles' weight with just one weight, and this weight is acting from the center of gravity of this object. Now, what does it mean, center of gravity? For an object that is regularly shaped and is uniform density, which means it's not made of copper on one side and plastic on one side, the exact center of the object is where the center of gravity of the object is. So predictable shapes like that, cylinder, the exact center here, the cube, the exact center here, ring is the exact center here. It is unique for you to note that the center of gravity can actually exist not within the body. For example, like a ring like this, right? It can exist, the center of gravity is actually in here. It doesn't even exist on the object itself. Which then begs the question, how does the center of gravity of a meter pipe that is non-uniform density then determine? Right? We determine the density, or rather the center of gravity of objects that are non-uniform via this method. Alright? Have the object have 3 holes poked into it. Alright? Once you have 3 poles, let's say I do not know where the center of gravity is. Let's say I'm assuming it's here, this point here. If I hang a string here, and the weight seems to act from here, this is the pivot, this is the force, this pivot and the force is going to cause this object to rotate. Now, when does the object stop rotating? It stops rotating when the object has turned in such a way that the center of gravity is directly below the pivot. Because when it is directly below the pivot, then the perpendicular distance, you remember this from your study just now, the perpendicular distance coincide, and therefore there is no perpendicular distance and therefore no moment. So whenever the object comes down and settles, it means that the center of gravity lies somewhere below this object. That means this is the exact center. The line here is somewhere at the exact center. So if I do again and I hang this here, I'm going to get another line where the center of gravity lies directly below this. If I do this again, then I will have another line where the center of gravity directly lies below this. So in this way, I have found the center of gravity of an object. Alright, so you can have a look here. This is what you would do. Hang the plumb line and you will have this center of gravity. Now, what is all this talk about center of gravity for, and why is it important? Alright, we are going to go into our last portion, which is the study of stability. How is an object able to return to its original position in this situation, and when does an object start to topple over when I'm tilting an object? So this deals with stability of an object. Alright, so this slide is important, so that's why I put a star here. So I'm going to zoom in quite a little bit because everything I've highlighted here is important. Now, when does an object return back to its original position? An object returns back to its original position when the vertical line through the center of gravity falls still within the base area. Then this will create an anti-clockwise movement which will cause it to return to its original position. So let me explain. The weight acts from the center of gravity. If I tilt the object a little bit in this situation, this will be the pivot point. If this is the pivot point and this is the weight of the object, this is the force. This force will cause an anti-clockwise movement like this. And this will then result in the object falling back into the original position. So this is what we term as something that is stable. Now, there is one point where the center of gravity, or rather the vertical line through the center of gravity, is actually just nice at the pivot when I rotate it. So when I rotate it too much and it comes to the point where the weight actually hits the pivot, when I release it, it by right should be balanced. But any kind of motion will, depending on the motion, will cause the CG to fall either to the left a bit or to the right a bit based on the rotation. It may then cause it to either topple or it may cause it to return back to original position. Which brings me to my last point here. If the weight, if I rotate an object and the weight line actually falls to the right of the pivot, so this was the original base area, right? So once this weight line exceeds the base area, then the pivot is here. It will actually cause a clockwise movement for this object and it will cause it to topple. So when the vertical line through the center of gravity, which is this line here, falls outside the base area, it will actually cause a moment which will cause it to topple. Now, you can use the term vertical line through its center of gravity. This vertical line through its center of gravity just means the weight line here. Or you can also use the line of action of the weight. The line of action of the weight is the same thing as the vertical line through the center of gravity. Alright, we say it's the same because the weight acts out of the CG and it acts downwards. So it's actually talking about the same thing. So this kind of phrasing that you cover here is important. So I'll put a star here because I think you need to memorize all of the way that it is phrased. Now, the stability of an object is a measure of the ability of the object to return back to its original position. Alright, and that stability depends on two things: the position of the center of gravity and the base area of the object. So we'll explore this a little bit more. Alright, so this is a diagram that we usually use to describe stable, unstable, and neutral equilibrium. A stable is one where it will always return back to the original position. So we will always describe a stable object like this. An unstable object is one where I push a little bit, it will cause it to topple and fall away from the original position. A neutral equilibrium is where once I push it to the right, wherever it stops, wherever I stop pushing, that's where the object will stop moving. Alright, so I'll show you examples of stable, unstable, and neutral equilibrium. So this is a stable equilibrium, a conical base here. When I rotate the object, for as long as the center of gravity remains within the base area, I will have a moment that will cause it to return back to its original position. An unstable equilibrium is like this. Any kind of force, any kind of tilt to one side will cause the center of gravity of the object, or rather the line of action of the force of the weight, will fall outside the base area, which is literally just this one tip. Once it falls outside, it's going to have a certain moment which will cause it to topple away from the original position. So this is an unstable equilibrium. Alright, neutral equilibrium, they use this kind of example, but my best example is just the ball. Because the ball, the center of gravity coincides with the pivot. So wherever I rotate it, even if I rotate it to this direction, the center of gravity will always hit the pivot point. So wherever I leave it, that's where it will stay. So we call this neutral equilibrium. The moment is always there because the line of action of the two forces, or rather the line of action of the weight, will always coincide with the pivot. So it doesn't matter. It will stay wherever you leave the object. So let's look at the effect of, or rather the center of gravity on the stability of an object. Remember, I think in like 3 slides before this, we talked about stability of an object, and it is defined as the ability of an object to return to its original position, and it is dependent on 2 things: center of gravity and the area of the base, or rather the base area. So let's talk about how, or rather what each of these center of gravity and the base area, what the effect it has on stability. So if I have an object that has a high center of gravity compared to an object with a lower center of gravity, lower as in physically lower to the ground, alright, this object here that has a highest center of gravity, if I rotate it to a certain point, it will cause this weight to fall outside the pivot, the base area here, which means once it's outside, it's going to topple. But if you have a lower center of gravity and I rotate it to the same angle, this weight is still going to be within the base area, and that will cause it to have a clockwise movement, which will cause it to return back to its original position. So the lower your center of gravity, the more stable your object is. So an object with a higher center of gravity is going to be a little bit more unstable. It's going to be a little bit more unstable, and it's going to topple when you rotate it even just a little bit. Alright, base area, if I have 2 of stools, one at the exact same height of CG, but one of the stools have a larger base area compared to another stool, then just based on how much I rotate it, when I have an object that has a thinner base area or smaller base area, once I tilt it even just a little bit, the center of gravity is going to cause it, or rather the position of the center of gravity the weight is going to fall outside the base area, and that is going to cause it to have an anti-clockwise movement, which will cause it to topple. While at the same angle, the weight here may still be within the base area or exist within the base area, and that will cause it to have a clockwise movement, which will cause it to return back to the original position. So the smaller the base area, the better your object is, or rather the worse the object is at keeping itself stable. So smaller base area, less stable. Alright, so this is a summary. I'm just going to run through very quickly with you. This is how you will answer why an object topples or why an object is able to return back to its original position. So an object is stable or unstable, or rather topple or does not topple, when the vertical line through the CG, you can use either the vertical line through the CG, or you say line of action of the weight falls within or outside. If it is going to topple, if it's going to be unstable, then we say it is outside the base area. When it's outside the base area, then there will be a certain moment, depending on the question, whether it's rotating this way or rotating the other way. It's an anti-clockwise or clockwise movement that will cause it to either return or cause it to topple. So this is how you would answer a question where they ask, will the object topple or will the object return back to its original position? Alright, so for you to have a stable object, you must have an object that is as low as possible, or the center of gravity is as low as possible, and the base area being as wide as possible. The wider it is and the lower the center of gravity, the less likely it is for it to topple. Alright, so I have an example here to show you. So I have two cereal boxes here. They look exactly equivalent to one another, but yet when I rotate the object by a certain angle like so, you will see that one object is going to topple and the other object is going to be able to return back to the original position. Sorry, let me do that one more time. So if this is the exact same angle, I'm going to release it at the same time. This one returns back to the original position while this fella topples. Now, obviously, the only reason why this, while they look identical, the only reason why this is able to return back to its original position while the second one on the right here is not able to return to its original position is because I have put a certain object at the bottom here, a heavy object. So this causes the center of gravity of the object to lower down because it's heavier at the bottom. Alright, and because of that, even when I rotate at the same angle, because of the CG is much lower, the line of action of the weight is still within the base area here, and therefore because of this, it is able to return back to its original position. While in this situation, because I didn't actually weight this one down, the center of gravity is direct center here. When I rotate it, once the weight falls outside the base area, then it's going to topple the other way. Alright? So let's run through some questions. Which of the following arrangement will result in the most stable? They, of course, obviously all have the same base area. So I'm looking for one where it's weighted a bit more at the bottom, because your center of gravity actually moves towards the direction of where the mass or most of the weight is. So if I put a lot of weight at the bottom, then the center of gravity is going to be somewhere here. If I put it all here, then the center of gravity is going to be high somewhere here. So when I rotate it by the certain angle, this fella, the line of action of the weight is more likely to fall outside the base area at the same angle compared to this one. And because it's more likely to fall outside the base area, then it's going to topple compared to this one. So this is the most stable configuration. Alright, so you can run through this and watch the video. You can find out, if you are interested, you can find out more about the ferry disaster and why, how moments had a part to play in this. And that brings us to the end of the chapter. So I hope that you found it helpful for me to run through the whole chapter with you. So that's it from me. Thank you.